Good morning, everybody in the lecture hall. Good morning, everybody on Zoom. Good morning, everybody watching us from the future. I'm going to continue. Today, I just would like to mention that I followed up on yesterday's question in the Moodle forum. So if you're impatient, you can already look now, but there's half hour of a delay until it gets sent. So you might receive an email after the lecture started. But if you have any follow-up questions on the follow-up answers, then do not hesitate. So first, I would like to make sure that you remember what I've told you yesterday. So what is a key value in HBase? I've told you last time that key values are everywhere. The key value model is everywhere. But in the specific case of HBase on the physical storage, what are the key values? My sound is completely sweet. I thought I pressed the button and now I realize I didn't press the button. So I'm thinking, is there anything that I need to be said that needs to be recorded? Well, I just discussed the questions, the previous question. So maybe I need to say the correct answer is the majority right here. And then I was taking it from there from yesterday. Thank you for letting me know that the microphone was not switched on. We store the key length and value length that's fixed 4 bytes, right? So why do we do it in this way? That's one of the answers I gave that will arrive by email soon, is that since this is fixed, you immediately know the length of the entire pair. So once you know you've parsed this, you can directly skip to the next pair efficiently. So this is the reason we put both of them here. And now that's where we stopped yesterday. This is what there is within a key. So remember that in a key, there must be the row ID, the column family, the column name, and the version. So the row ID is here together with its length. The column family is here together with its length. Again, remember that is elastic, that's dynamic, but this is fixed. That's dynamic, this is fixed. The column name, column qualifier, is dynamic, it's right there. It's dynamic. The timestamp is the version, so this is fixed. And this is called the tombstone. This is to mark as deleted. If you want to delete one, you create a new key value with a tombstone that says deleted. Bonus question, why don't we have the colon qualifier length? Yes? Yes, absolutely. You know the length of the timestamp, it's fixed. The key type is fixed. You know the length of the row ID key. You know the length of the column family. And you know the value length. So do you see you can just subtract, right? Who sees that? Right? Okay, so that would be redundant if we also stored the length of the colon qualifier. Okay, so that's what there is in a key, and all of that is sorted lexicographically. So this is why you see that it's first sorted by row ID, then by column family, and then by column name. And this is why I said the column filter, the column range filters, which also look at my Moodle post, the column range filter would not be super efficient because it's not sorted by column, it's sorted by row first. So you would need to look at everything and then filter out what you need. Okay. Then, don't be scared by what is going to follow. There are also blocks in HFiles, but this has nothing to do with HDFS blocks. This only has to do with creating some indexing structure of the contents of an HFile. So forget about HDFS. It's below. It's one level below. It's a file on HDFS, just a file. And within that file, we organize the key values in blocks of 64 kilobytes. Right? I'm going to call them H blocks because if I just say block, there's a risk of confusion, right? So the H blocks are the HBase blocks that you have in an H file. So this is just some amount of key values that are read together in a batch when you access them, when you read the content of an H file. So the blocks, the H blocks are elastic, meaning that they can be more than that. You could have even H blocks of 10 megabytes if you have a value that is 10 megabytes. So this is just a minimum size or a target size. But if you have small values, which can also often be the case, then you're going to have plenty of key values in that H block. Who is with me? Right, very good. So we organize these key values in H blocks. You can see them as mini partitions of the key values. And the reason why we are doing this is that if you look at an H file, in addition to just the list of key values, you're going to have some sort of index that tells you key 1 is the first key here, key 5 is the first one in this second H block, key 11 is the first one in the third H block, key 17 is the first one of the fourth H block. And what does it give us? Well, this here, it's part of the H file, but you load it into memory. So you have that into memory. And then you can see, let's say you look for key 14. So with a binary search, or you can also use tree data structures or whatever, you find it in here. You notice, okay, that has to be in the third H block because it's between 11 and 17. And then you immediately look at this H block right here. Who is with me? Right? Okay. Why is that efficient? Because we see that in many cases, we'll have a local copy of the H file because the region server is a client of HDFS, right? Do you remember where the first replica of a block gets stored in HDFS? Anybody? So I see plenty of raised hands. Maybe we take turns. It's the same as the client. Who is the client? The region server, right? So it means that the region server, by default, when it creates the H files, you will have a replica of the block on the same machine. So it means that this often is a local read from the local hard drive, where you can short circuit HDFS and directly read locally. What is the size of a local file on your hard drive, on your laptop? That's a block there is 4 kilobytes, right? A block on the physical drive. So it means that when you read from the physical drive, reading 64 kilobytes basically means that you're reading 16 hard drive blocks from your physical hard drive. Okay? Who is confused between the 4 kilobytes blocks, the 64 kilobytes blocks, and the 128 megabyte blocks? Oh, nobody. That's awesome. Okay, perfect. That's good. So yes, it's efficient because very often we directly read that from the hard drive, and here we have some index. In fact, we even have data structures that might have multiple layers of these indices, right? Yes. Technically, yes, but since we're on the same machine, we can cheat because we're on the same machine. So the block is a file on the local drive, and since it's a file on the same computer as you are physically, then you can read in 4 kilobyte blocks, right? This is called short circuiting because you're basically going around the name node based on information that you have. You're ignoring the name node, you're ignoring the HDFS protocol, and you're just cheating by directly reading from the local drive, right? And you can only do that if you have a replica locally. Otherwise, you would need to read over the network. Does it make sense? Yeah, awesome. Okay. So this is, yeah, I just had an animation for that, but I'm sure you understood, right? So you can directly and efficiently locate the key that you're looking for. Okay, so now I warn you that it's a complex lecture, and so in order to, I like to give you high-level lists or high-level overviews so that you can sort things in your brains. So these are all the levels of physical storage. It's just a nested representation. So we have the table, right? Gigantic table, could be petabytes with billions of rows and millions of columns. The tables are partitioned in regions, right? The regions are partitioned in stores, yes, by column family. So there's multiple regions in a table. There's multiple stores in a region. The stores are stored as what on HDFS? As, I'm hearing it. Yes, you were raising your hand. Yes, there's key values. They're further down. And in between the store and the key value, what do we have? The name of the file that we store on HDFS. So, there's multiple answers. So HFile, so you say HFile. What did you say? Yeah, so you agree with HFile? Yes, there's the blocks too. I have them too. Yeah, so you basically gave all the answers. We just need to put them in the right order. So we'll see, we have the H file here. So that was your answer. Then we have the H block, that was your answer. And then we have the key value, that was your answer, right? So you gave all the answers and we just put them in the right order. Who agrees with this hierarchy? Okay, awesome. So this is how you structure it in your brain, right, in your mind. So this is the way from the whole table all the way down to single key values. And here we talk about the persistent storage, right? What is persistently stored on HDFS. So take a good snapshot of this. Very important to keep your sanity on what we are presenting. All right, but now let me show you the problem. These key values in an H file, they must be sorted, always sorted. I think the technology that also exists in some companies, whoever worked at Google and heard of SS tables? Okay, nobody, yeah, that's some years there are people who know about them. So SS tables are basically exactly this. It's basically a structure where it's sorted strings, right? You have plenty of key values and you just sort them lexicographically. And that gives you a file. So that's an H file, a sorted list of key values. So far, so good. It's on HDFS, so we cannot have random access rights, right? We cannot just modify so easily this. We can happen at the end maybe, but we can't modify it. But then how do you insert new key values? Because I told you HBase has random access, random write access. So at any time, a user could say, I want to insert this. So I might want to insert a key 8.5, for example. What do we do? Because we don't have random access to HDFS, to the H files. Who sees the problem? Right? So the only way we could actually do it, if naively, would be to rewrite the entire H file. right? But the entire H file, that's a lot of data, right? That's not efficient. How can you do that so quickly? Well, now I'm going to show you how this is done. I'm going to show you the solution. So now I'm going to tell you what happens when you create new values, when you insert new values with a put in HBase. So I can't have enough of this one, so I had to show it again, right? That's the hierarchy. So basically, imagine we have HDFS. That's a virtual representation of HDFS because, of course, HDFS is a cluster of machines. It's a distributed file system, but it's all sitting on the local drives of all of the computers in the cluster. So on HDFS, we have the H files that are made of these 64 kilobyte plus H blocks that are made of key values, and then another H file. It's all sorted by ascending key, right? All sorted by ascending key. Now, I'm going to write a new key value. It means that a user used put and created a new value, right? So where do we put it? To be efficient, where we put it in the memory, right? So the key values that are just freshly created, we just put them on the memory of the machines, but not yet on HDFS, right? So now, if I want to write a new cell, I'm putting it in the memory. The name for that is MemStore. MemStore is the memory part of the store. That's what you have in the RAM of the machine. Then another one. I had a new key value. I had a new key value, but then at some point the memory is going to be full, right? Or we have some triggers that says, okay, now it's too much, right? So the memory is going to be full. What do you think we do when the memory is full? Maybe you can guess that. Yes? We write it to HDFS as a file. And what's the name of that file? An H file, exactly. So we write it as an H file. That is called flushing. We flush all of the key values in memory to an H file, right? Note that they must be sorted. So naively, you would have to sort them now, n log n. But what actually happens is that we do it proactively. So when you actually have them in memory right here, you already maintain a sorting structure in there. What kind of structure could we have to keep them sorted? I heard it. So we sort the keys, yes, but what structure, what data structure? Yes, for example, a binary search tree, right? Tree structures that basically maintain the sorting, right? And so that means that if I have such a structure in memory, what is the algorithmic complexity of flushing? Is it O of n log n? It should be linear, exactly. It should
put like one sorted list with another sorted list.
Mm-hmm. Yep, absolutely. You're correct. This is linear. The n log n was as we maintained the structure, right? We just kept updating it as we inserted the new key values in the memory data structure, in the tree structure. But printing or going through a binary search tree to print all of the values in the order, that's linear. Who agrees? Right? It's a simple visit of the tree. You just print all the leaves. Okay, so that's linear, right? So we kind of solved the problem by explaining that we actually only create the H files when the memory is full and we don't modify the H files in place. Plus, by the way, your question, how can it be there's multiple H files for the same store? This is how. Because every time the memory is full, you create a new H file and you keep the older H files. Okay? But do you see the problem that we've just created now? Because what happens if before I flush, there's a big crash, the machine crashes, and we lose everything that's in the memory. Who sees that then we've lost data? Right. So we need to solve that as well. You see, every time we solve a problem, there's another problem we need to solve. So how do we solve that? We solve it with what's called the write-ahead log. If you want to connect it with something we've seen before, it's like the edit log of HDFS. Remember, in HDFS, we keep an edit log of all the changes made. Well, we do the same thing here. So what is done is that whenever you want to create new key values and put them into your tree structure in the memory, in the MemStore, before you do that, you also store these new key values to, guess what, an HLog, right? An HLog is a file that has all the key values that you freshly inserted. Is there a question on Zoom?
I have a question on Zoom. When you say that keys must be sorted, that implies that they should be sorted inside a store, inside an HFile, or inside a block, question mark.
All three, everywhere. It's sorted in the MemStore because we maintain some binary search tree or a sorting structure. It is sorted within each HBlock, and it is also sorted across the entire HFile, right? Exactly like as shown here, you see? It's both sorted within HBlocks and across the entire file. Did that answer your question?
Yes, thank you.
Yeah, all right, yes?
Are the H files sorted one after another? Let's say I'm trying to look up the value. Do I have to look up in all H files?
Yep.
See where it is? Okay.
Yeah. So I'm repeating for the people on Zoom to hear, if you want to look up a value, you have to look at all H files. Because to be even more precise in the answer I give, it's sorted within the HBlock and within the H file, but it is not sorted across different H files, right? Because these are the freshly created ones. So it means if you want to read, you need to read all the H files plus the MemStore. That's a very good point. Yeah. There was another raised hand, I think. Do we have another raised hand? Okay, I don't see it anymore. Okay, and on Zoom, it's all good. I answered your question. Okay. All right, so we flush when it's full, and just in case there's an electricity shortage or a crash of the machine, we write these values to an HLog. But then you're going to tell me we're back to square one because we anyway wanted to write an H file. So what's the difference between an HLog and an H file? Can anybody tell me the difference between an HLog and an H file? Because both contain list of key values, right? Yes? Yes, so we don't have H blocks like we have in H files. And another difference? Or anybody can tell me another one? Yeah? It is not, well, it is, yes, it is not sorted in the sense lexicographic. It's sorted differently, I would say. But your answer is correct. This is the sorting that is different. Because in an H file, it's sorted lexicographically. In an HLog, it's sorted by order of insertion, right? The HLog is just a journal, like this one was inserted at that time, and then this one was inserted, and then this one was inserted. So it's the order that is different between the HLog and the H file. Who is with me? Right. Now, do you see that for the HLog, we just need to append key values because it's the order of arrival. So whenever there's a new key value, we just append it at the end. That's good because HDFS is good at appending things to files. So HLog is on HDFS, and we just append every time there's new key values, we just add them. There is one such write-ahead log, HLog, for each region, server even. I'm not so sure about the granularity if it's even split by region, but in any case, at the region server level. Okay? Any questions? Yes?
Are there duplicate keys with different H files?
If you do not override any versions, there cannot be because the version is going to be different. You have a timestamp. So every time you create a new key value, it will have the new timestamp, right? So you just create new versions. But I do have this open question that I was asked, like what happens if you override an existing version, and that I don't know, right?
Yes, but it's not clear to me why the files are not sorted across different H files.
Ah, okay. So you mean why is it not sorted across different H files? Imagine, as an example, that somebody wanted to play and just inserted the odd values, right? So 1, 3, 5, 7, like as column names, right? Or as values, 1, 3, 5, 7, and so on. And then somebody inserts even numbers. Do you agree that the even numbers will go first to memory and then we'll flush the even numbers? So then you would have an H file with odd numbers and an H file with even numbers, but you see they're intertwined, right, in the sorting, right?
Okay, but what if odd values get into the MemStore?
They don't. The old values, they're on disk now. The MemStore is when the user creates new cells, creates new values, right? It's with a put. So these are the old ones that pre-existed, that have been inserted before, and the new ones that just have been freshly inserted come to the memory store. But there's no way back, right? It doesn't come back from an H file to the MemStore. That doesn't exist. Right.
But how does the system know that I have put odd values and then I will put
it doesn't know. It doesn't know. It just creates a new value with a new timestamp. Yeah, and that's why it's efficient, because it's just adding them. Okay. Yeah, go ahead.
Let's say we have the same key value in multiple H files. So we select then the one with the most recent timestamp.
Yes, that is correct. You need to read everywhere, and then you take the most recent timestamp, right? That is absolutely correct. I even have slides coming about that, right? Okay, any more questions? All right, but I will do some more investigation regarding your question and what happens if we create a new version to try to give you even more precise answers regarding the mechanism when we add a new key value that potentially already exists. Right, so I'll get back to you on that. Okay, so then I'll continue. So we have the write-ahead log. And you agree that now, if, and after the H log, then we forward it to the MemStore. You agree that now, if the computer crashes, then we're fine, because we just play again the H log and recreate the MemStore from the H log, right? Who agrees with that? Right, okay. So when do we flush? Well, there's many different reasons why you would flush, but it all has to do with reaching threshold. For example, you could see that you have a max MemStore size. If you reach that size, then you flush. You could also flush when the total aggregated MemStore size on the entire cluster reaches a threshold, because maybe you could consider that that's risky when the overall cluster starts having too many values in memory. Or you could also decide that it's based on the size of the write-ahead log that could be full, right? A maximum size for the H log, and then you flush. Okay, it's jointly, right? Whenever one of these is reached, then you flush. So now I have a slide for what you've just said, basically. So when we want to read, yes, there's a question there. That is correct, and I even have animations about that. There is no fixed number of H blocks in an H file. That varies. It depends. Because again, we just flush when the memory is full. That's the only criterion. So you might have cases in which the memory has a small number of big key values, 10 megabytes, or you can have cases in which you have a huge number of very small key values, right? And that changes the number of H blocks. Because with very large values, you would have less H blocks, because the H block extends past 64 kilobytes. And when you have small values, then that gives you more H blocks. Okay, yes? There's only one MemStore for this store, for the column family and region. Then maybe that was your question. If you're responsible for multiple column families, then indeed you would have, well, on the logical level, you could consider they're separate, a logical MemStore for every column family, right? And then that would create an H file for every column family. Yes, absolutely.
We have a question on Zoom.
Yes.
Does a flush always result in just one H file?
Yes. You take all the key values, sort them, and bam, H file. You get an H file. Yeah, that is correct. Okay. Any other questions? Don't see any others on Zoom. Also that. Okay. Okay, so now I'm coming to what you said. So indeed, when we read, imagine now a user is doing a get. We want to get some value. If we want to get some value, we need to read from everywhere. It could be everywhere, literally. So we read from this H file, we read from that other H file, we read from the MemStore, and we gather all of the key values. Then we might notice that some of these key values are actually the same cell. It's the same row, the same column family, the same column value, but just different versions. Then we take the latest, right, to return to the user. Except, of course, if the user specifically requests an old versions or multiple versions. But this is when we take the latest versions of all the cells and return them to the user. Who understands that? Who understands why we need to look everywhere? Okay, very good. Because there's never a guarantee that you wouldn't have data in all the H files, right? That was there very long ago. So in other words, if you try to locate a specific row and column and you don't find anything in memory, that doesn't mean it's not there. It could be on disk. It could have been created a week ago and have been flushed to disk, so you always need to check if it's not on disk. Okay. Okay. Yes? Yes, so absolutely. So what you are saying is that there is no reason why we would have to read every H block, and you're absolutely correct, because we have an index over the H blocks, right? So if we're looking for specific row IDs, we could determine that we only need to look at this and that H block within an H file, right? You need to look at all H files, but you might just look at some H blocks determined by the index, right? As a complement to your question, there is a trick known as the Bloom filter. Whoever heard of that? Bloom filter. It's a hash-based way of telling for certain that an H file doesn't contain some key value, right? So you have an efficient way. If you look for a specific key, you can hash it, and the Bloom filter will either tell you for sure it's not in this H file, or maybe it is in this H file, right? It's asymmetric. It's a maybe or it's a no. If it's a no, then the Bloom filter allows you to completely skip the H file, right? Then you don't even need to look at all the H files with the Bloom filters, right? And this will be in the exercises. I don't have them in the lecture. It's a very, very clever trick with hash functions. Yeah. Does it answer your question? Yeah, very good. Any others? Okay. So when we read, we need to read from everywhere, except if the index tells us it's in a specific H block, and except if a Bloom filter tells us for sure that there's nothing in a specific H file. Then we skip the file. Okay. But now we have a new problem, because if I keep using the system again and again and again and again for weeks, for months, for years, then as you can imagine, the number of H files is going to keep growing, and at some point it becomes unmanageable, right? There's too many H files to look at, and we have a problem. But we have a solution to that problem, and the solution is called the compaction. We take the H files and we just combine them to a single big sorted H file. What is the algorithmic complexity of this? Is it n log n? Because we need to sort. Yes, it is linear because we are just merging sorted list. It's the second half of the merge sort. Who remembers the merge sort? Right? It's the second half of the merge sort. We already have pre-sorted H files, and we just merge them. It's a concurrent traversal. You just traverse them with pointers in each, and you just linearly write the new H file. Who agrees it's linear? Right? Okay. Very good. So by compacting, we further reduce the size, the number of H files that we have on disk, and that keeps getting more efficient, right? Okay. Now a bit of terminology and theory. You don't have to worry too much. Very high level. I'm just giving you names. You might remember from the relational database systems lecture, data modeling and data management. Who remembers that lecture? Right. So you learned probably on B+trees, which are a way to build indices that very efficiently locate values on a local disk. And when I say a local disk, I mean the local disk on your laptop, not HDFS. So with B+trees, we basically very efficiently look up single values. Do you agree it's seek time bound, it's latency bound, because we look up very small amounts of data, and so what constrains us is the time it takes for the disk to rotate and reach the head, right? So it's seek time bound. Who agrees with that? Who doesn't agree with that? Who doesn't know if they agree with that? Okay, so picture a large number of seeks, a large number of lookups. It's all the people that query your database, point queries, very local. You query specific values, and every time you get the latency of your local drive. But this is a classical database management system in which you have B+trees. In white column stores, the structure that we have is known as the log-structured merge tree. Log-structured merge tree. It's a bit of a tongue twister to say, but I managed. And here, the bottleneck is no longer the latency, as it would be for the B+tree. The bottleneck is the throughput. And in fact, I've already shown you that, and I just didn't call it an LSM or log-structured merge tree, but this is what we saw here. Because since now we store all of this sorted list of key values, we keep them in memory when we write them, and then we flush HFile by HFile, we flush to disk. This is, in fact, batch processing. This idea of accumulating things to do and then doing them all in a single batch is called batch processing, right? So this is batch processing, this idea of flushing and compacting. And so that means that if you are in a database system that is dominated by flushing and compacting HFiles, then what dominates in terms of performance is the throughput. It's the speed at which you write these files to HDFS that dominates. Who agrees? Okay, very good. And the reason it's not latency is that these files are big, right? These files are big, so you will have a bit of latency when you write it, but then you spend a lot of time writing it. So this is why I'm saying the bottleneck is in the transfer time, in the throughputs, in transferring data all the way to disk. Okay, so these are the two competing structures, right? Classical database systems, B+trees. White column stores, we have log-structured merge trees. And so the idea of the log-structured merge trees, more precisely, is that you have some first level in memory, that would be the MemStore. Then you have a first level on disk, that would be when you have flushed once, so that's a flush. And when you compact them into even larger HFiles, then you have yet another level, right? MemStore, flush it to a small HFile, compact HFiles to even larger HFiles, then you compact again, and you see the HFiles become bigger and bigger, right? So the recent HFiles, the recent data will be in small HFiles, the old data will be in large HFiles. Who sees that? Right? Very good. So now I have an animation for you, but I have to insist that it's a theoretical animation. This is, in practice, it's not going to happen like this, but this is to give you the feeling. So imagine that the MemStore is full. What do? We flush to an HFile. The MemStore is full again. What do? We flush again. So we have a second HFile. So now imagine again, that's for my theoretical experiment, that we have this rule that says we cannot have two HFiles that jointly exist. So what do we do with them? We compact them to a larger HFile. Do you agree? It's twice as big, right? Now the memory is full again. What do? We flush. You see, you're getting used to it. So we flush. The MemStore is full again, so we flush. But now we have two HFiles of the same size, roughly, so we compact. Now we again have two HFiles at the same level, so we compact. Now the MemStore is full again, so we flush. Now the MemStore is full again, so we flush. We have two HFiles at the same level, so we compact. The MemStore is full again, so we flush. The MemStore is full again, so we flush. And so, well, that's it, right? So you get the idea, right? That's how it works. So what you basically observe here is that there is a whole hierarchy of layers, and in fact, this is what I was showing on this slide right here, that you have all of these layers. And basically, as time elapses, you just keep pushing and pushing and pushing the HFiles to the right. A few years ago, somebody made an excellent remark. It's like the game 2048. Who plays that game? That's the same thing. It's 2048. So this is basically how it works. So you have the fresh data right here, and you have the very old data right there. Who remembers that from information retrieval? We had similar structures in there, right? So the IDs are similar, right? So this is a log-structured merge trees. Checking the time. We still have a few minutes. Yeah. All right, and I like to joke saying that we might even find dinosaur fossils if we go to the very deep and large HFiles over there, because that's the data from long ago. Okay, but now it's the theory. In practice, what actually happens, it resembles that. In practice, we are not so strict about these powers of two and the things. We just distinguish between minor compactions and major compactions, right? So there's some sort of, a bit like the garbage collector in Java, right? There's basically tools and daemons that monitor all of that, and they periodically compact the HFiles. So you have the minor compactions that just merge them, and then you have the major compactions that might also prune deleted key values and older versions, right? So in the major compactions. For whom is that clear? Right? But the behavior resembles the animation. That is a bit of a caricature, but it resembles this behavior. I have only a few more slides to go. I'm just considering if I need to do it now and possibly create confusion, because that was already a lot to digest. No, maybe I could actually stop here for today with the log-structured merge trees and these 2048 games. So that's it for today. Maybe you can come to me at the break for the question. Do read the Moodle forum with the follow-up questions for yesterday, and I will also follow up on the today's questions to investigate for you. Thank you very much. Have a good day and good exercise session, and see you next week.